Hello, we're in the OLC kitchen today, and that usually means there's a practical angle to some of these videos, and today is no different. I want to work out how to make my home smart meter a bit less naff. Most folk in the UK have one of these things. It's not really the smart meter itself, but it allows you to visualise what the smart meter is thinking. In my instance here, it has 642 watts being consumed. That's how much power my house is consuming at the moment. And that's fine and all, but actually I'd like to develop a system where I can track this value in real time. Now, my energy supply doesn't provide that functionality with this meter, nor do they provide some sort of API I can access to do so. I'm going to have to build my way out of it, which will require code across several different platforms. You see, part of my problem is this instantaneous number doesn't tell me what's going on in reality in my home electrical network. Are things having high inrush currents? Are things operating efficiently? When are devices coming on? This is information I can't get from my energy supplier. They bill me accurately, I have no complaints about that, but the app they provide on the mobile is rubbish. And I think I can do better. Welcome to Under the Stairs of OLC Studios, and this is my smart meter. You can see the mains coming in from the street, going into the meter itself, and this is going to record how much energy I'm using, and it sends it back to my energy supplier. It's not my property, I'm not allowed to touch this, and I wouldn't want to. It's got mains from my street going into it. From the smart meter coming back out, it goes to my consumer unit with all of my fuses and gets distributed around the house. Whilst I was sat here staring at my smart meter, I was wondering, what are all these blinking LEDs for? Why are some of them green, some of them red? Then I had a quick look at this front panel, and we can see this blinking red LED says next to it 3,200 impulses per kilowatt hour. This blinking LED light is the equivalent of the disc spinning in the older versions of our meters. It's telling me in real time how much power I'm consuming. If I could somehow trace what this light is doing, I'll be able to see what my house is doing regarding its energy consumption. And so that's what this video is about. I'm going to design a small widget that I can fasten to the side of my smart meter, monitor what that blinking light is doing, and then upload that information to some server where I can access it anywhere in real time. So let's get started. Now, I know some of you will be thinking, hey Javid, why not just go on Amazon and buy one of these devices? They already exist. Well, I don't really want to. I don't want to subscribe to another service from another unknown company for a device that's only going to last for a few months whilst they harvest as much data as they possibly can from me. I'm also interested in building a more home-based network of devices, of things and Internet of Things and that sort of stuff. It's a lot of fun and it's interesting, and it keeps sort of my stuff private, which I like. I thought it would be useful to briefly outline the plan. Here is my smart meter. The smart meter has a blinking LED on the front. I'm going to use a microcontroller and a simple detection circuit that will detect when that light blinks and then signal the microcontroller to do something. This microcontroller is going to use its onboard Wi-Fi module to send messages to the internet. Hopefully those messages will end up at my server. This server happens to be running a WebSocket server. Now, if I open a browser and point it at my server, it can get information about these pulses and somehow display that information on a website. Of course, this browser could be on my PC, but it could also be on my phone, which means I can access the information about what's going on with my smart meter in a convenient manner as I walk around the house without needing to create my own app. There's three distinct pieces of code here. We've got a program running on the microcontroller, which is going to be in C and C++. We've got another program running on the server, which handles the WebSocket connections, which is also going to be in C and C++. Actually, less of the C. Finally, we've got a website, which will fundamentally be HTML and JavaScript. Frankly, that's a lot to get through in one video, but I don't want to turn this into a series, so I'm going to go very quickly through these components, but I will upload most of the resources to the GitHub later. For example, for the microcontroller, I'm going to be leveraging the ESP32 libraries and FreeRTOS. The website I'm going to keep very simple, but I will be using chart.js. But the one that's going to offend the most of you is what I'm doing with the server. At the lowest level, I'm going to be using ASIO. I've used that on the channel plenty of times. But in fact, I'm using somebody else's WebSocket library, which is based on ASIO, WebSocket++. And in fact, I've wrapped that up into something OLC based, which I will do a deep dive into in some other video later this year. So really this video is more of a summary of what I did rather than a deep dive into how I did it. Fortunately, it's really not complicated at all. As a first pass, the algorithm I'm going to implement is not clever at all. In fact, it's rather naive, and we'll see why later. Ultimately, I'm going to break time into 1 second intervals. For that 1 second, every time the LED on the smart meter blinks, I'm going to count it. And then I'm going to return how many counts there were per second to the server, which should hopefully yield a graph like this. Most of the time pretty similar, but when I switch the kettle on, suddenly it goes very high because we're getting a lot more pulses. Recall that my smart meter has indicated it will do 3200 impulses per kilowatt hour. And so the more pulses I see in a second, the more energy I'm consuming. The time interval is constant, so for every second I'm sending data out to my web server. That might seem like a lot, but in reality it's not. It's just a handful of bytes. And my web server will then relay that to any browsers that are listening. So I should get a nice graph updating every second. This is the microcontroller I intend to use. It's an ESP32. It's really cheap and really available, and there's quite a bit of stuff out there on the internet on how to use it. I will say actually I don't like them very much, and I find the development environment a little bit, well, unrefined. That said, when I say it's cheap, it's incredibly cheap. I think this one cost me about £7. And it's pretty cool because it comes with a reasonably good processor clocked at about 240 MHz, and it's got integrated Bluetooth and Wi-Fi modules and a USB-C connector. It also has easily accessible GPIO via all of these pins. And in fact, I bought to go with it this breakout board, which makes accessing all of those pins even easier, but it also allows me to plug it into a power supply. The breakout board, in fact, came with the ESP chip, so the whole thing combined was about £7. When the two are mated, it's a little bit smaller than a credit card. Unusually today, I'm going to be programming in VS Code. It's like a lightweight cut down version of Visual Studio, but it's really just a text editor. However, it's becoming quite a popular tool for programmers and for manufacturers of little widgets like the ESP32 board, because they can design an extension which then sort of bundles a load of tools into this environment. And that's exactly what I'm going to do. By installing the Espressif IDF extension, it installs the appropriate tool chains to convert the C and C++ code that I'm going to write into the correct machine code that the ESP32 can run. Now again, my apologies for those that expected a really deep dive into the code. I've just not got the time for that today. But I am certainly going to review what code is here. ESP32 apps have an entry point called app main. Now I know I want one of the GPIO pins to be configured as an input, and more so, I want it to be configured as an input that can trigger an interrupt. This block of code here defines the behavior of that particular pin. I want to interrupt on the falling edge of the signal. I want the pin to be an input. I want the microcontroller to pull up the signal, should it be floating around the place if nothing's connected to it. And this is the pin I have chosen to be my input. The GPIO config function uses this information to specify the I/O configuration. Next, I want to associate something happening on that pin with an interrupt service routine, ISR. Essentially, when that pin goes low, I want it to call this function, GPIO ISR handler. Here is that function. I have a great big global variable called gimpulseCount, and every time this interrupt service routine is called, it increments that variable. With the GPIO configured, I then enable the Wi-Fi, enable the WebSockets, it's okay, we'll come back to these in a minute, and then sit in a never-ending while loop. In this while loop, I wait for 1 second. It's important to remember here that there is actually a real-time operating system running in the background. So when I delay in this loop, I'm not blocking the whole device. Once I have waited for 1 second, I'm going to output to the console, via the USB debugging cable, the current value of impulse count. I'm also going to send the current value of impulse count via the WebSockets to the server. I'm then going to reset impulse count and then sit waiting for another second. This gives me my 1 second intervals. I should probably take a little bit more care regarding writing to impulse count here and writing to impulse count in an interrupt service routine. But I'm happy that the increment instruction is reasonably atomic anyway in this environment, as is assigning 0 to its value. And that's it. That's the end of the program. Now, let's go and have a look at these trivial functions, Wi-Fi Go and WebSocket Go. And I'll be frank, these took a little bit of investigation to get running. If we look at the includes for this program, this is all in one file. We can see at the top I'm including the real-time operating system. I'm also including some headers which allow me to configure the general purpose input-output. I've then got some includes for handling the Wi-Fi. The environment already has lots of example code for interacting with Wi-Fi, and to be fair, it did make it all quite trivial, which is remarkable for a small embedded micro. The Wi-Fi capabilities of this device are quite sophisticated, no wonder why it's quite popular in the hacking community. You can see here I've lifted code directly from their examples, and I can pass in the ID of my Wi-Fi network, and I can pass in my Wi-Fi password. Their example code uses the non-volatile storage. This is memory which persists even though there's no power on the device. I think it uses this memory to expedite connections to Wi-Fi and Bluetooth and other such things after future reboots, because the speed of connection is very quick. Either that or it's storing my credentials for later to upload to who knows where. We then need to initialize the network stack. This is the stuff that handles the TCP/IP lovely goodliness. Finally, we initialize the Wi-Fi itself. We'll have to have a look at this function. Don't forget we're running a real-time operating system, so we can shove things into tasks to just sort of happen in the background. This is necessary in an application like this, so we're not blocking things all the time. And connecting to Wi-Fi and things that are unstable may require several attempts or searching or at least tuning in, none of which can be done in a deterministic amount of time. This function was taken entirely from their documentation. Fundamentally, it initializes the Wi-Fi module, and it registers an event handler, in this case Wi-Fi event handler, to be called when events happen in the Wi-Fi module or general IP events happen in the networking module. The Wi-Fi module will handle the connection to a Wi-Fi network, but then the network stack needs to handle the negotiation for the IP address. We'll have a look at this event handler shortly. We populate this Wi-Fi configuration struct with the name of the network and the password and the type of authentication being used, configure the Wi-Fi module with that information, and tell it to go. We're then going to sit and wait for lots of different things to happen. In this case, we want to connect via the Wi-Fi and we want to get an IP address. Once the module is connected and identified, we no longer want to listen to those events anymore. They could just become a nuisance. The Wi-Fi event handler, which we've pointed to, handles multiple different event types. We can connect to the network and disconnect to the network. We can see here we can attempt multiple times to connect to the network. But we can see fundamentally that once we have connected to the network and we have been given an IP address, we will set all of those bits which allow our Wi-Fi init function to continue and exit, signaling that we have successfully connected to the Wi-Fi network and have been given an IP address. The final piece of the puzzle is talking to a WebSocket. Once we've got an established network connection, then we need a nice interface which will package things up in WebSocket speak and transmit it via the network to our server. The ESP provides facilities for this in WebSocket client. Fortunately for us, this is a much simpler function than the Wi-Fi. We need to configure our WebSocket client with a URI or URL, a port number, and a security certificate, because you'll notice I'm actually using secure WebSockets. This security certificate path points to a location in the memory of the ESP32, and that memory will write directly this information. Now don't worry, I'm not giving anything away here. You can go to any website that's got a security certificate, go to its settings and download this file. And I needed to do that for onelonecoder.com. The WebSocket API is really simple. I initialize the WebSocket client with that configuration. I register an event handler, in this case called WebSocket event handler, that's going to listen to any WebSocket events. And then I start the WebSocket client. Again, we're running on a real-time operating system, so this will now run away in the background. The WebSocket event handler is reasonably trivial. We'll get an event and some data. The event could be we have connected to the server, or we have been disconnected from the server. Some data has been transmitted to us. In this case, we don't actually care because the device itself is going to be transmitting the data. Any data it receives, it can't do anything with anyway, so it does nothing. Or we have an error state. If you've done any WebSocket programming, you'll recognize these 4 states because every WebSocket interface exposes them. You can see that we don't actually care about any WebSocket events at all. All we're doing is displaying things to the debug console should those things occur. In our 1-second interval loop, once we've got a count of impulses, we call WebSocket send impulse count and send that value to the server. Here is that function. First, we check are we actually connected to the WebSocket server. If we are, construct a string with the impulse count that we've passed into this function, and then call the WebSocket client send in text mode function to send that string to the server. Now you'll notice I've constructed a special string here called drb42%d. The %d is a placeholder for the integer c which we're printfing into this string. The drb42 is, well, it's a little bit of a password thing that I can use to make sure that the thing that connects to the server is something I expect it to be. In this trivial example code I've used 5 ASCII characters. I could use 64 ASCII characters and make it almost impossible to guess. So yes, admittedly a little bit complicated for onelonecoder.com, but we initialize some I/O and attach it to an interrupt service routine. We tell the Wi-Fi module to start working. It will go away and create a network stack and engage the radio module itself. And when both the radio module has connected to an access point and we have got ourselves an IP address, this function will continue. We then go on to engage the WebSocket module where we tell it where to connect, what port to connect, and the security information necessary to connect to that server. Once that connection has been established, we then enter a tight loop where we wait for 1 second at a time, count pulses, and send that pulse count every second. The microcontroller has many pins, but I'm interested in pin D4. Here you can see I've also labelled the voltage at 3V 3 in and ground. To test our circuit, I'm going to add a switch between D4 and ground. When the switch is open like this, D4 is technically floating. That's why internally in the microcontroller we've added a pull-up to the power supply. So when the switch is open, our signal is high. When we close the switch, it goes low, because we effectively short D4 to ground. When I work with microcontrollers, I prefer to have switches this way round, because it's unlikely you'll do any damage to your microcontroller by connecting an input pin to ground. But it's quite easy to accidentally connect your input pin to some other voltage, which would potentially detonate your microcontroller. Relying on the microcontroller's pull-ups to get the high logic values is reasonably safe, although not always appropriate. But for us, we'll be just fine, and it's this falling edge here which we're going to use to increase our counter. The Visual Studio Code extension that we've installed provides these tiny little buttons at the bottom of the screen which do all of the major things. So let's save our stuff and build the project. Despite having a few rough edges, it does all kind of work quite well. When you get to this screen here in the terminal at the bottom, you know you've been successful in the build. We can then click the tiny little flame button, which basically flashes the device and then monitors the debug for output. That's what I'm going to do now. I've plugged it in. As you can see here, I've connected the ESP32 to my computer via this USB cable, and I've also connected up a switch between ground and D4. Let's click the little burn button. It's successfully built. Now it's going to start programming the microcontroller. We can start to see lots of information that the Wi-Fi module is outputting on the debug output terminal. We can see that our WebSocket has successfully connected. We can also see the string impulse count 0 being output over and over and over again. This is great. I'm now going to press the button. and we can see that for that one interval there was one button press. If I repeatedly press the button like this, we can see that the intervals have different value counts. It's actually quite difficult for me to press the button with any consistency because it's a cheap, nasty button. See, the best I got there was 7 counts in 1 second. More importantly, we only get an impulse count when I press the button. I'm pressing and holding it now, and we can see that the count has counted 1, and then I'm going to let go, and there's no counts at all. Given we've implemented no debouncing or anything, I'm quite pleased that for now this microcontroller is doing what we need it to do. Now, I was going to go and build a small PCB to implement the light sensor. There are several ways to go about doing it. I could use a light-dependent resistor, but all of the cool kids today are using a photodiode or phototransistor. As I was looking around to see which photodiode's component to actually use, I stumbled across a complete ready-to-go module. And this is it. It's a tiny PCB with a photodiode at the top, some biasing resistors and some capacitors, and a comparator. The comparator will output a digital signal if the light shining on the diode is above a settable threshold set by that small pot that's on there. The thing is also powered by 3V3, and it can output an analog signal too if we're interested. In short, this is exactly the circuit I would have designed anyway, and it was less than £1 on Amazon. In this instance, genuinely no point in me reinventing the wheel. So why am I not using this straight away? Well, simply because the button right now is easy to control whilst we're debugging things. We can swap this in for the switch later. Right, the hardware is established, we know it can connect to the Wi-Fi network, but it has been successfully sending messages to a WebSocket server somewhere. Let me show you how I did that. After trying a few different libraries, I settled on WebSocket++ by Zaphoid, and this is the GitHub for that particular library. Sadly, the main branch doesn't appear to be maintained anymore, but the develop branch is quite active. WebSocket++ is a richly featured library. It's got lots of examples and high quality documentation, and it's built upon the ASIO platform. It's also header only, and we like that on OneLoneCoder. Whereas its focus is on WebSockets, what it doesn't mention here in its list of features is it also acts as a rudimentary HTTP server. We might come back and look at that at some other time. A reasonable question to ask might be, why are you using WebSockets in the first place? Why not just use regular networking server technology? Well, firstly, I want to be able to push things to the websites that are connected to the server, and secure WebSockets are a good way to do that. Secondly, and rather selfishly, myself and a few guys on the Discord server have been creating some WebSocket backend technology for the Pixel game engine, which should allow you to have multiplayer Pixel game engine apps running in the browser. And to that end, I'm going to frustrate you all now by showing you some code which isn't available yet. Sorry about that. In OneLoneCoder tradition, we're creating a header file that wraps the core functionality of this WebSocket++ library. We might remove our dependency on that library in the future. WebSocket++ is very thorough and very deep, but we only really want certain parts of it to work reliably and work consistently for our needs. Although still a work in progress, this is the OLC WebSocket server.h file. The intention of this header file is to make your own secure WebSocket servers with ease. And it'll automatically handle things like account banning and rate limiting. Similar to the Pixel game engine, we're providing a base class where the user will override particular methods that they need. We provide functions for client management, and we have functionality for communicating between the clients. Our main WebSocket server application couldn't be any simpler. Here it is. We create an object of type server and we start it. The object server derives from the OLC WebSocket server abstract base class. It's abstract, so server has certain obligations to fulfill various methods. During the construction of the server object, we have to define the port that we're going to listen to, paths to the security certificates that we're going to use, and we define this mysterious constant, which we'll come back to later. The first function we're going to provide an implementation for is onClientConnect. To have gotten this far, the connecting client mustn't be on our address blacklist. All I'm going to do is display the address of the client and return true to accept the connection. I could do some additional filtering to reject the connection. To accompany a client connection, we have a disconnection function. This is called when it is determined that the client no longer has a connection to the server. We display a message to indicate as such. The next function is called when the client sends data to the server. Before this function is called, any data sent to our server needs to be validated. So let's just scroll down here a little bit and have a look at this function. OnValidate incoming allows you to have a quick peek at the data before doing anything with it. If it looks like the data is acceptable, we can return true from this function, or we can return false. Depending on how the server is configured, receiving invalid data can do certain things, like get you blacklisted or banned or timed out. My validation is very simple today. I firstly check that I'm getting more than 5 characters worth of string data, and then I compare those first 5 characters with the magic password we're sending part of the ESP32 string. Since the communications channel between the ESP32 and the server are secure, this is a reasonably crude yet quite effective way of making sure that the client is at least attempting to behave itself. If it looks like I'm receiving legitimate information from the client, I return true, which then allows this function to be called. This function is very simple. It constructs a JSON string consisting of an X and Y coordinate. Along the X-axis I have time. You can see I increment a tick value because I'm expecting to receive something from the client every second. In the Y-axis, I look at the not first 5 digits of the string that was sent and convert them to a number. I then write that JSON packet to all connected clients. Hopefully they're going to be things like browsers. The device itself will also be one of those clients, but as we saw, it doesn't do anything with that information. Finally, I have this onUpdate function, which currently doesn't do anything. But this function is called every 0.1 seconds. In this simplistic energy monitoring project right now, I'm just relying on clients connecting and sending data to cause things to happen on the server. For the rest of the time, the server will go quiet. However, if your server is also implementing some game logic, you might want to update that game logic in a reasonably thread-safe way periodically, and that's what this onUpdate function allows you to do. So by specifying that magic constant at the start, every 1/10 of a second my onUpdate function is called. I could set that to be whatever tick rate my game would require. And so for the WebSocket server, that's that. By using our new header file, look how easy that was. One of the things I will give Visual Studio credit for is the ability to remote debug on a hosted server such as this. I can edit the source files directly and then compile them and start the process running on my server. So now we have the device sending out a count of how many times the button is pressed. I have a WebSocket server listening to that device, and it's going to issue that as a JSON package to anything that listens. We now need to work on the bit that listens, and I'll admit that web development is not exactly my strong point. But I do know that to do good web development you need a good web kit, so I'm going to go and get mine. I hope it's still in here. Oh, God. Oh, God. See, web development kit. Careful now, careful now. Oh, there it is, good. Looks like it was nice and clean from the last time. Right, let's do some web development. Joking aside, I just don't do web dev often enough to be any good at it, and by the time I've learned something it's already out of date. And so let's say I more than lean on certain folk of the Discord server for their help and expertise. I simply don't have any. But I know enough to scrape by. I have created an index.html page. And this is it. It doesn't do very much. I'm going to import the chart.js package to visualize the counts in time, and I'm linking to my source file, index.js, which we'll have a look in a moment. The rest of the HTML file consists of not very much. It's a single canvas called energy usage chart and a blob of text called what's now. When the HTML document has been loaded, it goes and calls my JavaScript function onLoaded. I'm going to get some flack for this. So apologies, here is my index.javascript file. In it I define the function onLoaded. And I go and grab the part of the HTML document that's going to display the chart. I then use chart.js's charting tool, which is excellent by the way, to define a scatter plot in the X and Y axes. I'm expecting later on to have all of this in instantaneous watts, because that's the actual useful measurement for the energy consumption of my house, so that's how I'm labelling it up at the moment. As part of the chart, I've disabled all of the animations and fancy stuff. It was making the data look a little bit obscure. But here's where we get to the interesting stuff. I'm going to create a new WebSocket to my WebSocket server. And some of these functions may look familiar to you. In the event that we have opened a socket, I'm going to set a connected flag to true. I set the same flag to false when we disconnect. I'm not using that flag for anything at the moment, but it might come in handy later. The function that matters today is this onMessage function, which is called when the browser receives some data from the WebSocket server. I know that the data coming in is a JSON object, so I parse it. I'm also going to output it to the console so I can debug it. I know that the X component of my JSON object was the tick count, and I want my chart to scroll as data is injected at one end and lost at the other. The data for the chart is stored in an array, I think, called graph, and each time I receive a JSON object, I push that object to the graph to give it an X and Y coordinate. If there are more than 100 elements in the graph, I call the shift function to remove the first element of the array. You can tell I know what I'm doing. I also want to display on the HTML page the last value that I've received, so that's just the Y component of the JSON object. I then rescale the graph in the X-axis and tell the chart to redraw itself. And as you can see, that's it. Not much to it. After I've uploaded these files to my web server, I can go and point a browser at it. And here we go. And I've got the development tools in the browser open so we can see what's going on. We can see a graph with a line on it. And we can see the value counts is equal to 0. The Y component of our line is also equal to 0, but our graph is ticking along at approximately 1 second intervals. We can see in the console for the web page that we're outputting our JSON object, and it's just an increasing counter. If I jump on over to the bench and press the button, the device sends one count to the web server, and the web server echoes that packet back to anything that's connected, and we can see it there in the graph. Let's do it again. Tick. Very nice. It's also really quite instant. I'm really pleased with how well that's come together. If I press it several times, many as I can, if I keep pressing it, we can see that we're getting various values appearing on our graph. Smug mode on. I'm really pleased with that. That's very satisfying. I've got 3 different bits of technology all talking to each other depending on the button press. And that's a useful state to be in because we can see that we've got all of our ducks in a row, to steal an English expression. The next task is to connect our light sensor to this and replace the switch. I got myself some of these female to female DuPont leads. Very, very cheap, but very convenient. And I'm going to connect this up to the power supply. We'll use purple for power, blue for ground, why not, and green for digital output. Nice, they all line up. I'll just disconnect the device for a second whilst I'm doing this. Nicely, the device will connect to the web server by itself. So actually powering it down like that shouldn't cause me any problems. Right, I want to make sure I get these right, so power can go on the middle one for D4. Power, ground, and green was signal. That's right, green was signal. Isn't that really nice? I quite like that about this expansion board, is that they provide power, ground and signal for each I/O pin, so it makes connecting a module like this very simple. The cables have quite a bit of rigidity, so I've just wrapped it round on itself so I can see what's happening and keep it all neat and tidy. Let's power it up and take a look. Well, we can see that the module has got some power. Its LED has lit up. I don't think you can see that it's green on the screen. And if I cover up the sensor, we can see one of the LEDs going out. More importantly, as I cover it up, we can see that the graph is also counting how many times I cover it up. In fact, it's actually counting loads of times. Looking at the values on this graph, we're seeing 29, 67, 34. That's because the threshold of this comparator has absolutely no hysteresis whatsoever. And there's all sorts of ambient light. As the shadow of my hand is going over the photodiode, it's not a distinct black and white on or off decision. That may come back to haunt us. But for now, at least we're seeing some sort of communication, and we can see lots of pulses being sent. That's good. I just wanted to confirm what was going on with the photodiode using my picoscope. It's a USB-based oscilloscope. It's okay for simple things like this. So I've got a probe on the output signal, and I'm just going to run my finger over the front whilst triggering it. And what I'm going to try and capture... There we go. So we can see it's actually really noisy, that digital signal there. There's lots of chatter, as it transitions from high to low and low to high, and that's to be expected. It's because of ambient light, reflections, all sorts of things. The photodiode is very, very sensitive, but the comparator looks like it has absolutely no hysteresis at all, which is a bit sucky. The truth is, I don't think that's going to matter much when we're blasting an LED directly into it in a highly controlled light environment, and that's really what now the 3D design is going to provide for us. Interesting stuff. Now, even though you couldn't tell it from my workbench, I do actually like to work quite tidily. So I'm going to package this up now in a 3D printed housing so I can attach it to the meter without too much mess. I'm going to use an external power supply wall wart because I don't have a computer down there under the stairs. To design the housing, I used Autodesk's Fusion 360. I'm familiar with the Inventor environment, and Fusion 360 is reasonably well priced for my needs. I started by designing the main chamber to house the ESP32 module and its expansion board, and you can see it's got these sort of 4 lugs that can sit to the board properly. I then cut a small hole in it for the DC jack input. I made a lid which would work just by compression. There we go. Nice, that's the first part done. The second part was to construct sort of this appendage that would house the light sensor. The hole at the bottom is precisely the right width for the LED. The idea is this will capture the LED light coming from the smart meter and channel it into the photodiode. This too has a cap on the top so we can keep the light out of it. Put some cosmetic finishing touches to it, and voila, I was quite pleased with that. The next step was to put it into Bamboo Studio and orientate it so I could print it efficiently. You can see I used the tree support, because I like the tree support, and here it is printing. Oh, look at that, isn't that nice? Sorry about the lights changing all over the time. I was too keen and kept shoving a torch in there to see what was going on. Printing black in a dark environment is tricky. So I've got my final device here. It's in its 3D printed case. I've got a socket on this side for a 12-volt wall wart that I'm going to power it by. You can see here, I'm just looking on my screen, the little photodiode that's going to receive that blinking red light. Obviously the ESP32 is housed within this. I'm going to go and plug it in. Let's go and install it. To start the installation process, I've left off the cap that allows me to see what the module is doing. I can't see the LEDs on the front directly, but I'll see them light up nonetheless. And that's quite useful because, as we saw upstairs, one of the LEDs on the front blinks when the input signal is high enough to trigger that comparison. Connected to power, we can see now that the green power light is on. You can also see the red lights on the ESP, but I'm less bothered about that. To actually stick it to the meter, I've used a semi-adhesive pad on the side. So I can just hopefully get this lined up, make sure that the sensor is over the blinking red LED, and I can verify that that's the case, because now you can see it when it blinks red, we also get a green blink on the PCB. I'll now finish the job by putting the cap back on. That'll also stop any ambient light from entering the system. At last the system is installed. Let's go and see what it's doing. So to start with, I'm just leaving it at ambient. You can see it's ticking along, returning sometimes counts and sometimes no counts. There's not very many counts happening, but that's good. Hopefully that means there's not much energy use going on right now in my house. I don't really know what the wattage is at the moment. This is just a display of counts per second. How many times that LED blinks on the smart meter. So I'll turn the kettle on. There we go. And oh, good. So we're expecting the number of counts per second to increase, simply because the number of impulses per kilowatt hour should imply that because now I'm using more kilowatt hours, that count should go up. I'll turn the kettle off and we'll go and try something else. Let's go and try the oven instead. Now I know that my kettle was about 3 kilowatts and I know that the oven is about 2.5 kilowatts. I've turned it on, but really all I'm seeing is, well, the same again. It's certainly more energy being consumed, but I can't quantify it sensibly at all here. And this is a fault of that naive way we chose to recognise the impulses. Let's just analyse this for a moment. Here I have a graph with time along the x-axis and kilowatts along the y-axis. The black line indicates me turning on the kettle and then me turning on the oven. In this toy example, my kettle consumes slightly less power than the oven, but what we've got along the x-axis is also these red lines, which represents every time the LED on the smart meter blinks. So we can see when we're counting in intervals, we get 0, 1, 1, 0, 1, 1, 1, 2, 1, 1, 1, 1, 1, 1, 1, maybe 2, 1, 1, 1. The blinking LED is reasonably low frequency, so most of the time we might actually not count anything at all. This means we get these bursts of counts that we do see as it's catching up. Worse still is we're basically throwing out resolution. We can't discern any difference between whatever this device is and whatever this device is. Yes, on a macro scale we can, but really I'd like to know precisely what the wattage is being consumed by my house at any given time. We need to think differently about how we interpret what the blinking LED means. We know we've got 3,200 impulses per kilowatt hour. We can convert that to kilowatt seconds by multiplying by 3,600, as there are that many seconds in an hour. To keep this clear, let's just call this constant A. To work out our instantaneous kilowatt value, we can take A, which is in kilowatt seconds, and divide it by the time taken in between pulses in seconds, which means these effectively cancel out, leaving us with an instantaneous kilowattage of our constant divided by our interpulse duration. This is in kilowatts, so we're going to multiply the whole thing by 1,000 to turn it into watts. So our watts becomes 3,600 over 3,200, all of that divided by our interpulse duration in seconds, and all of that multiplied by 1000. On the ESP32 microcontroller, I'm going to do something different with the interrupt service routine. Instead of just counting the pulses, I'm going to measure the time taken between the pulses and add that value to a queue. Here I've created the handle for the queue, and here I've created two variables to store the new and old times. When the interrupt is called by the falling edge of the sensor, I get the instantaneous time since boot up, work out how long ago it was since I last called that function, and then I queue that value. It's important to queue this value from the interrupt service routine. The last thing I want to do is go and get the WebSocket trying to do some communications during the interrupt service routine. I was always taught that an interrupt service routine handler should exit as quickly as possible. They're typically considered very high priority and will block everything else from happening. Fortunately, the ESP32 library provides some functions for thread-safe queue handling from interrupt service routines, and that's exactly what I'm using here as I deposit the delta into the queue. In my main while loop now, I wait until there is something in the queue to receive. It's quite nice, this function, because it will block until there is data deposited in the queue. When there is data in that queue, I convert it into milliseconds as an integer, and I send it using exactly the same WebSocket function that we created earlier. So now, rather than sending the counts per second, I'm sending the time in milliseconds between pulses. You might think that this is overkill for such a system, because there's going to be a lot of pulses coming out of the smart meter. Well, I'm not too worried about it, simply because in the microcontroller land and in the time system of our entire electrical system here, there is still an age between pulses. We're not going to saturate anything, and I'm certainly not going to consume so much power as to cause any problems. Well, at least I hope not. In the JavaScript file for the website, I'm just displaying the counts. I'm now going to calculate the instantaneous wattage using the equations we've just seen. So I'm going to ditch this part of the code and replace it with this instead. Recall that the packet coming into the website now is the time in milliseconds. Well, I want to convert that to seconds. Then I calculate the instantaneous wattage. I'm going to assume my house never consumes more than 40 kilowatts. If I do get back a value that high, there's something's gone wrong. It's probably been a divide by zero somewhere, so I'm not too fussed about it. I then push the wattage to the graph and display the last recalled wattage calculation. Let's see how it all comes together now. Here you can see I've included my smart meter in the shot, because that should be an accurate calibrated value of power consumption. It's ambient at the moment. You see, I've just turned the kettle on, and look how much more responsive my graph tracking application is than the smart meter. They don't read precisely the same values. I'm not entirely sure why, maybe a small calculation error somewhere. However, I like the responsiveness of my application compared to the smart meter. I'll now try it again with the oven, and we should see the same thing. After a few days of trialling this, one of the things I did learn is I actually have a faulty appliance at home. It has a high inrush current and it's doing it several times a day. It's actually costing me about 75 pence per day, which you think, well, that's nothing at all, don't worry about it. But I would not have been able to detect it on the smart meter alone. That being said, I can now go and replace the device. Hopefully this application is already starting to pay for itself. And so there you have it, quite a project, but now I can remotely monitor the energy consumption of my house via, well, anywhere I like, because look, I can put it on my smartphone and I can see the same graph being generated in real time. I've really enjoyed this project, but I do regret that I've had to do a very shallow dive into the technical detail of the various components. I think as we get more accustomed to doing slightly more embedded projects this year, I'll get better at it, so don't worry about it. Anyway, in the resources below, I've created a folder in one of the GitHub repos that contains the 3 core elements of the source. And if you've enjoyed this video, a big thumbs up, please. Come and have a chat on the Discord server. There's lots of nerds on there too. Until then, have a think about subscribing. Thumbs up. See you next time. Take care.